Welcome to the AI Cafe. Today we have the speaker Mihai Dogariu. He's assistant professor at University Politehnica of Bucharest. So great you're here, Mihai. Hello. With his talk on realistic financial time series generation. And my name is Carmen McWilliams, and next to me is Teresa Felchens. We both work for Grassroots Arts, and we are the moderators of this cafe. And please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers all express their personal view and opinions. This is not necessarily the official AI for Media project opinion. And what's the cafe about? It's about networking in Europe. The cafe is an online forum to gain insights into the European AI scene. Participants get the chance to share knowledge and experiences. I'm very happy also for all the participants today in the cafe that you're here. Great you're coming in. Great you're joining us. As always, please send us your questions. This is an interactive session, which means when the speaker makes his presentation, please write us your questions and we will ask them to the speaker after his presentation. So now we're coming to the main point, to our speaker today. Mihai Dogariu is an assistant professor at University Politehnica of Bucharest. He received his PhD degree from the same university in 2021. He's a member of the AI Multimedia Lab and has been actively involved in more than 10 research projects on various topics from the multimedia field. His research interests revolve around unsupervised learning algorithms, data generation, and learning with limited examples. So it is a pleasure to have you here, Mihai. I will now give you the moderator role, and then you can start to present to us. One moment. Yes, I gave you now the moderator role.
Okay, just a second.
Yes. And as I say, please send us your questions.
Perfect.
We see it. Perfect. Perfect.
So you can see my presentation, okay?
Yes. Oh, perfect.
Yep. Okay. So hello, everybody. My name is Mihai Dogariu, and Carmen already made a very nice presentation. So introduction, sorry. So thank you very much for that. Today, I would like to talk to you about realistic financial time series generation. So this might sound a bit like a complex field, but I'll try to summarize all the technical information down to the strict necessities. And I would like to insist more on the, let's say, more tangible parts of my work. You can also see here my website. I am part of the AI Multimedia Lab. It's a very nice lab that we have at the Politehnica of Bucharest. And if you are interested, you can access the site and you can see more information there. Okay, so let's dive in. First of all, let's talk a bit about what is a time series. So if we are talking about financial time series, the first thing that we will have to introduce is this term of time series. So basically, when we think of time series, we think of a data set that tracks a sample over time. So this should be the most basic definition about time series. And I'm sure that everybody has seen graphs that look similar to this one. This is a graph which contains the stock market evolution for several companies on the US stock market. I have generated this with a tool available from Yahoo. So this information is openly accessible by everybody. Okay, so on graphs like this, you usually want to track how the stock market evolves. As you can see here, these three companies are very well known. This is Tesla, this is Amazon, and this is Google. So I specifically added these ones because they are very familiar for everybody that has ever heard of the US stock market. Okay, so just by looking at this graph, you can see some interesting aspects. The most shocking one, let's say, is that during this time, almost every company or almost every index that we have in the stock market has suffered a drop. This drop is, of course, connected to a worldwide event because it affected the entire stock market. And this one specifically was related to the pandemic. So you can see here that when the pandemics struck almost the entire world, so most is well, especially the US part, all the stocks dropped. Okay, so this is just to have let's say an insight on what we are working with. So these are the financial time series. Why do we want to study this financial time series? Well, there are several use cases that can be let's say helped by a thorough study of the financial time series, and these are the following. So the first one is portfolio management. This is very useful when companies or hedge funds want to start investing in a certain company. So they want to expand their portfolio. Then also the metadata management is also very useful because if you understand how the data evolves from time to time, so if you can find some data seasonality, then of course you can let's say take advantage of that situation. So you can rely on this type of metadata that lies beneath what can be easily observed from a stock market graph. Then, of course, the main aspect of financial time series study is to make some models, some AI models preferably, which can predict the stock market evolution. So these are the forecasting models. So, of course, if we talk about financial time series, we need to talk about money. So this is the biggest incentive for studying this problem, because you would like, of course, to forecast where to the stock market will evolve. So whether it will rise, then you can buy some stocks. Whether it will drop, then you can sell some stocks. So of course, everything revolves around this main problem: stock market prediction. And of course, if you want to build some AI models for any of these use cases, like any other AI models, you need large amounts of data. So it all comes down to this aspect, that you need lots and lots of data for your AI model to train and to process in order to have very accurate predictions. Well, of course, there are some problems with gathering this large amount of data. And here I would like to present three of the main problems. The first one is that the financial time series must be unified homogeneously for each country. What does this mean? Is that each individual country has its own stock market. And even if the data available for each country is openly accessible, so anybody can access it, it is very, very difficult to gather the data about each company from each country, and then also line it up and process it in the same format. So bringing all this data to a homogeneous format is very, very difficult. If you want to do this for more than one country, then it's already a very, very expensive process. then you will have a limited number of examples. This number of examples is limited by the number of companies that have been listed on the stock market. So if there are, let's say, 1,000 companies on the stock market, it is impossible for you to create more than 1,000 financial time series. And the last point, also very important, is that you cannot haste the data acquisition, meaning that you have to wait for the day to end, and at the end of the day, just at that moment, you can see how the stock evolved. So if you have the history for, let's say, the past 20 years of one company evolving on the stock market, then it is impossible for you to bring to your data set more than 20 years of data, because that is the physical limitation of this type of data. You cannot take data from the future relating the time series. Okay, so there are numerous problems with this data. So the solution that we found to this type of let's say drawbacks is to generate synthetic financial time series. So if we are to generate synthetic financial time series, we will really like them to be as close as possible to real data, such that we solve all of these three problems. And in order to do so, we used some generative models, some generative AI models. The ones that we focused on were the GANs, the GANs, so the generative adversarial networks, the variational autoencoders, and the Gaussian mixture model networks. I will explain a bit about each one of them in my next slides. So the financial data has several characteristics. The first one is more of a definition. It represents the chronological evolution of several indicators for each company. Now, these indicators are the following: the open price, the high price, the low price, and the closing price. Together, they form the OHLC. So they are very well known in the financial domain, in the financial industry. Open represents the price that the stock had at when the stock was opened during that day. High is the maximum value that it attained during the day. Low is the minimum value throughout the day, and close is the closing value at the end of the day. Out of these four, the most important one and the most commonly used in the literature is the closing price. So this is how the closing price for two different companies, AOS and ADB. ADB stands for Adobe. Looks throughout the past 20 years. So we can see that the closing price initially maybe started in the same range for these two companies. Then for AOS reached a high of, let's say, $70 or $80 for each stock, whereas for Adobe it went up to 300. So it's a very large discrepancy between these two. We can observe a very high both inter and intra-class variability. So if we want to treat more companies in the same way, then we have to find a way of normalizing these values. In order to normalize them, we use what is commonly known as logarithm returns. The logarithm return is simply the logarithm of the ratio between the closing prices from two consecutive days. So here CI is the closing price in day I, CI minus 1 is the closing price in the previous day. Then we extract the logarithm out of this ratio and we obtain the logarithm return. And by switching to logarithm return, we can see that these two companies, which had a very different and very distinct behavior, now look almost the same. They are both in the same value range, and we can see that there are no more, well, let's say that we can easily characterize both of them inside the same value range. Okay, so Now, a few words about the dataset that we have used. This entire work was carried out together with Hana International. So Hana is a financial group from South Korea, and they provided us with the data set to work on, and also they monitored all of our progress, and they told us, let's say, they helped us on the financial part. We were in charge with the engineering, with the research part, and they were in charge with the financial part, so that in the end we can have the best of the two worlds. Now, the dataset that we have used is the S&P index. This one is very popular, is basically the US stock market, and it has been provided to us by our financial partners, so from Hana TI. Then, for this dataset, we have used the granularity at a day level, so we have daily entries for those four measures, OHLC. And in total, the dataset consisted of 1,506 companies from 1980 up to June 2019. Now, something important about this dataset is that it contained only companies which are still active on the stock market. Meaning that if there was a company which at a certain point went bankrupt or was bought by another company, that company does not appear in our dataset. So we are aware that this is some sort of a bias towards the more performant companies, so companies which are still active. And these companies started at some random times, let's say, in the past. So we'll have something that looks like this. On the right side, we have the index of each company, and each horizontal line represents the financial time series of that said company. As you can see, all these lines can start at different times in the past, but what is common to all of them is that they all end up at the present time. So since this dataset was up until June 2019, each company will have data from June 2019. Now, another important aspect about this dataset is that it contains unequal segments, let's say. Because as you can see in this picture as well, these companies started random times in the past, all end up at the same time, but throughout their history they can have some irregularities. Like as you can see here, if you make a snapshot in January 1981, then there are only a few companies present. If you go 1 month into the future, there is one more company which appeared on the market, and so on. So we must find a way to deal with these unequal segments in a fashion that is also beneficial for our research. So what we did was the following thing. In order to set up our data set, we took all the companies and selected only the last 20 years of data. Everything that was before June 1999 was thrown away. So we are not interested in that data. It's already very old. That stock market behavior is not, let's say, up to date anymore. So that information is also quite obsolete. We are not interested in that type of information. So we kept only the last 20 years of data. Then we adapted a windowing mechanism, meaning that we selected windows of length 250, which roughly equates 1 business year. Business year meaning working days. So 250 working days, it's roughly 1 entire year. And we made the following processing. First, we extracted all the values inside such a window. And as I mentioned before, all of these segments with red belong to companies which appeared sometime during that time frame. So from June 1999 to June 2000, there are several companies which appeared on the market, which were listed on the stock market exactly inside that time interval, meaning that we will not have a full segment available for them. So there is this question: what should we do with this data? There are two possibilities. One is to fill in the missing data with some values, and the other one is to drop that segment, that incomplete segment, entirely. We went on the second approach, so we dropped all this insufficient data, and then our let's say entire length segments data set for one interval looked something like this. We compacted this such that after extracting the first window from our dataset, we ended up with 855 companies. So out of the total 1,500 companies, only a bit more than a half of them had data available for June 1999 up to June 2000. Then the next step was to slide this window. The sliding stride that we used is 30 working days. It's roughly 6 calendaristic weeks. And after sliding the window with 30 points, we performed the same extraction process again. So again, we extracted all the data, we dropped every narrow entry, so every incomplete segment, and we ended up with a certain amount of complete segments. This number, of course, increases with time. So if at the previous step we had 855 companies, now we had 870 companies. And of course, this will grow with each iteration. So in the end, we had a data set that looked like this. Here is the first subset, then another subset after we slide the window, then another subset if we slide again the window, and so on. And we had here two types of approaches. I will present both of them. The first one was to consider the entire concatenation of these subsets, one big data set. So this is the first approach, considering this entire concatenation of subsets, one big data set. Out of this data set, we randomly extracted batches of fixed length segments. This was because we wanted to perform GAN training, and GANs work only with a fixed dimension of data. This was done because we wanted to adapt as easily possible GANs from processing images, which is our main field of research, to GANs which process a financial time series. So now a bit of some words about the generative models that we used. As I said before, we wanted to adapt GANs from processing images, which are bidimensional, three-dimensional. So we have 2 dimensions if we are talking about black and white images, and 3-dimensional if we talk about color images. And we switched from processing images to processing time series. Time series are 1-dimensional. So in order to do so, we used several architectures, several GAN architectures. I will not go in full detail about this, but we have used multi-layer perceptrons, which are, let's say, the least complex type of GANs that can be used, and also fully connected GANs. Fully convolutional GANs. Okay, so the general framework for a GAN is the following. We have a noise vector which goes through a generator, and this generator manages to synthesize a sample. This sample can be anything that your application wants. So it can be an image, it can be an audio signal, it can be an entire movie, let's say, and so on. So it depends strictly on your application. For us, it was a financial time series. So the generator generates such a synthetic sample, and then the discriminator has the job of telling whether the sample that he is seeing is either real or fake. And this discriminator is trained with both real samples and synthetic samples. So the job of the discriminator is to tell if the sample that he is seeing is real or fake. The job of the generator is to trick the discriminator into believing that the synthetic sample is real. So this is a very brief description of how GANs work. And another important thing that we stumbled upon, and this was very problematic, was how to perform the evaluation of the synthetic samples that we managed to generate. Because in image generation, there are two, let's say, metrics that can be used. You can either use the FID or the inception score to tell whether an image is well synthesized or not. Whether for time series there is no such thing, there is no such metric. So after a lot of discussions with our financial partners, we ended up with some metrics that we proposed as a premiere, let's say, because this has not been tried before. So we focused on two types of metrics. One is qualitative and the other type is quantitative. For the quantitative metrics, everything was okay because we adopted several information theoretic metrics, and it was easy because these metrics ended up telling us that, okay, this synthetic sample generates this number as a metric which can assess whether it is good or not from the discriminator's point of view. Whereas for the qualitative metrics, this was very, very problematic because qualitative metrics means that you have to subjectively assess whether this metric is met or not. So whether your synthetic sample approaches real samples from a subjective point of view or not. So for the qualitative metrics, we had this set of measures. The first four central moments, the autocorrelation, telling whether or not our PDF follows a heavy tail distribution, whether the volatility clustering is observed or not, and also the TSNE and PCA visualization. So people who work in AI are certainly accustomed to most of these metrics, and they know how such a graph looks like. Just in order to give you an insight on this, visually assessing such results takes a lot of time. Let me show you why. So this is how we assessed the first four central moments. With red, we have the measures that were obtained on the real samples, and with blue, the measures that were obtained on the synthetic samples. So this is how a graph for the first four central moments looks like when we compare the real samples with red with some badly synthesized synthetic samples. So this is not something that we would like to see. This is something that we would like to see. So subjectively determining whether our synthetic sample is close to reality or not means that we have to look at this kind of graphs and manually select each such model that results in, let's say, a spread of points for these four metrics, which is very similar to the real ones. So it's very difficult because you have to manually go through every iteration that your model manages to synthesize, and then determine whether or not that iteration was good just by looking at these types of graphs. So this was for the central moments. Here is another example that we used for everything that contained autocorrelation. Again, we have graphs. On the upper part, we have how the real one should look like. On the lower part, we have how a badly synthesized one looked like. And here is how goodly, let's say, a well synthesized sample looked like from the same point of view as the one above. For determining whether we have a heavy tail distribution or not, this is how it should look like. So here there are two PDFs which ideally should overlap. With blue, you can see just here at the bottom that where they are a bit different, that the blue one is a bit wider, so the real distribution is a bit wider than the red one, which is the synthesized distribution, but they are still very close to each other. This is not what we want to see. So this is something that came out wrong from the synthesizing model. But again, this had to be manually performed. And the last type of synthetic evaluation from a subjective point of view is the cumulative sum for each financial time series. So this is how it should look like. We have here the three graphs for we have a graph for three different companies, and with different colors you can see that they are very random. They are not similar to each other. Whereas one of our bad models managed to synthesize something which is identical for all types of companies. This, on the other hand, is a good model which managed to synthesize different behaviors for three different companies. And in the end, we are looking to let's say touch all of these subjective metrics at the same time. So we are interested only in models which manage to synthesize good samples from all of these subjective perspectives, and also from the objective perspectives. So the quantitative metrics have to also have good values. So in the end, our results were summarized as this. Here we have all the qualitative metrics, and here we have either a check mark or an X mark. The check mark means that we managed to be close to the real behavior of this metric, whereas the X mark means that we were nowhere near that particular metric. On the right side, as I was saying, we have the objective ones. So here we have only numbers, and we are always interested in the lowest values that can be attained with any of these four metrics. So in order to summarize, we found out that there is one type of model which will behave the best from this set of models. And we selected this one as being, let's say, our go-to model when synthesizing financial data sets, financial time series. But then we came up with another idea. Going back to the data set, where we had three different subsets, we thought to, okay, we might be doing this wrong in the first place, because we randomly selected companies from this data set. So a random selection of segments from this data set. And when you are doing that, you are losing some type of correlation. So in order to not lose that type of correlation, we treated each subset as an individual batch for our AI algorithms. Of course, now these batches, so each subset has a varying length, but that was not such a big problem, what it helped us do was to preserve the cross correlation on each batch. And besides this, we also added another interesting idea related to the regime that the companies were working in. I will explain this in just a bit. So here is a bit of information about the regimes. I promise you that this is the last part with mathematical formulas. So what we want to do is the following. Here we determine the mean of all the closing prices in a certain day. So the mean of all prices in a certain day is just like performing the mean on the stock market on a vertical line. So if you have, let's say, 2,000 companies, you draw a line, a vertical line, and then you perform the mean of the intersection between that vertical line and all of your stock market. Then the rolling mean is the mean value of the previously mean values computed on the past capital L days. So it's just going back in time and performing the mean on the entire segment. And now the regime is computed in the following way. If the current mean is greater than the rolling previous mean, then you have an uptrending regime. Otherwise, it is a downtrending regime. And for the financial time series, you end up with something very interesting, which is that the market is generally growing. This means that 2 out of 3 points have an uptrending regime, and only 1/3 of your entire market is downtrending regime. Okay, so this is about the regimes. And then again, for the generative models, we added some more information because we've seen that the Wasserstein models performed better. So we added only Wasserstein models this time, and also a spectral normalization GAN, and besides GANs, also variational autoencoders and Gaussian mixture model networks. I will not go into a lot of details with all the models. What I would like to present to you is how VAEs and GMMNs work. So their general scheme is the following. For the GMMNs, the generative moment matching networks, we have here the input, which goes through an encoder, and after obtaining the latent vector, you take that latent vector through a decoder and obtain a reproduction, hopefully an identical replica of the input. Now, after training such an autoencoder, you want to have a different network, which is the GMMN now, which can take one input, one random noise input, and transform it into a latent vector which mimics the same distribution as the latent vector of your autoencoder. And by generating new samples and passing them through the GMMN, you are hopefully obtaining new latent vectors which will be decoded into new samples which follow the same distribution as your input. So this is, in theory, what the GMMN should do. Then the variational autoencoder behaves quite similarly in the sense that you have the input, which goes through an encoder, and the encoder encodes your input into a vector containing the mean, one containing the variance. And here you have a random value, which will be multiplied with this variance. And by adding them together, you obtain a latent vector, which will be decoded into a synthetic sample. Again, ideally, this should be the same as the input. So at the output, it should have almost the same data as at the input. And then you control the generation of new synthetic samples with the help of this random noise, which is epsilon on this graph. Now, this time we observed that there is some need of adding some supplementary evaluation metrics. For us, these were the cumulative sum, the trend ratio, the trend prediction accuracy, and this was all both qualitative and quantitative. So we have it in both sides. Now, the results look like this. I know it's a lot of information, but we then summarized it into only a group of 5 different models. And out of these models, we again found out that there is one particular model which behaved better than all the rest of the models. So these were the variational autoencoders. They were the perfect choice, let's say, for any type of synthesis or for any type of metric that we have assessed. And then in order to test our samples, our synthetic samples, we came up with a prediction framework. This prediction framework works like this. You have an entire set of 20 years, our data set, which we divided into chunks of 8 years. For each such chunk, we split it up into 7 years for training and 1 year for testing. In this prediction setup, we just used an bidirectional 2-layer LSTM in order to see if we can improve the results of such a prediction framework with by adding our synthetic samples to the data set. So here are the results. The baseline was obtained solely on real samples. So our prediction framework had an average accuracy of 50.04%, which is almost equal to random choice. So this is the major problem of financial time series prediction. You are never certain of the prediction that you do, that it will be good or bad. Then by adding our synthetic samples to this training data set and testing again only on the real data set, we obtained quite an improvement for each individual model that we have used. Now, I know these numbers don't seem very high, but our financial partners told us that if we reach 52% accuracy, then we shouldn't tell anyone and just go use the algorithm and get rich. So 52% was our gold standard. Anything close to 52% is sure to be working very well on the stock market. So this is quite different from other fields where you expect accuracies of 99.97%. In the financial field, even 51% is a lot. So anything that is above random choice is sure to help you. Okay, so we proved with this that adding synthetic samples will improve the prediction capacity. And then the conclusions for our work were that we managed to find some metrics which point out the bad models, some metrics which point out the good models. We always wanted to choose Wasserstein over vanilla implementations. We found some models which fail miserably in every possible aspect. And again, we found some models which work very well for our problem. And finally, we've also addressed some open challenges. So we found some problems which are still open and have not been solved by anyone so far, meaning that finding an optimal model architecture for generating such synthetic samples is very difficult and still an open challenge. Also, the cost function in order to generate such samples, the evaluation process has not been discussed by anyone so far, and so we were the first ones to introduce to even question this evaluation process. And also, it would be very interesting to model some real-world major events, such as the financial crisis, the pandemic, or the war that is going on right now, and the effect that it has on the stock market. And lastly, to apply this type of algorithm to cryptocurrencies. So this is not yet solved. Okay, that would be all. Thank you very much. If you have any questions.
Thank you very much, Mihai. This was very interesting. And yes, there are questions from the audience, but I will start first.
Okay.
It's more provocative question. Are you already rich?
No. No, we were in charge only with the research part. The financial part was left for our partners. So even if we made such a model, we cannot benefit from it, unfortunately.
Okay, thank you. Now, Teresa?
Yeah, I do have a question. I'm actually going to start with one from the viewers because that was something I asked myself as well. Is there a way to analyze firms leaving the market?
Yeah, it should be. It should be possible as well, because when a firm is leaving the market, of course, that you will see a downwards behavior for that market. So I think that people can access this type of data. It's openly accessible, so you can access it on the internet. But if you have also somebody which is already in this domain behind you to help you with that, they can provide you with such a data set. But it is more difficult, of course, than accessing firms which are already in the market.
Maybe Teresa ask the next question from the audience.
Yes. Yeah. It's a longer one. Is there a large difference in the models or data sets required to train short-term, medium-term, and long-term financial time series prediction algorithms? Or do you always predict based on a specific time window?
Well, the difference in implementation is something negligible. You just change the size that you take in, but the behavior changes a lot, because if you want to predict for the next day, then you have one type of algorithm. But if you want to predict the next 10 days, maybe, then everything has to be changed. But if you are doing the same thing that we did, but you just extend those periods, then it's just a minor tweak that you have to do in your model training. Everything else stays the same.
Then should I ask another one, or do you have questions?
Yes.
Okay, great. Then we have one that says, apart from the closing prices, why not considering the volume of the corresponding assets as an additional information?
That could be useful. We've tried with a multi-channel model, which took in information about the open, the high, the close, and the low prices, but not also the volume. So the one that worked with 4 types of information, that needed a bit of more work, but in the end, yeah, we obtained some interesting results with that as well. Not the best ones, but they were somewhere in the upper middle part. So we still found some models which behaved better than that one.
Then we have one from Alison. When you are I think I don't know the word. It's either spelled wrong or I just don't know the word. Concatenating. Does it say anything to you? Okay.
Sorry, no.
I'm sorry, I don't know the word. Maybe you could
maybe concentrating,
and then I can repeat the question, and I will just read another one. Yeah. Do you include any company metadata or market metadata in your models, or is all of the predictive power coming from the time series alone?
No, from the time series alone. But it's a very interesting question, because if you add some sentiment analysis, or if you add, let's say, the news that run around on Twitter and all that, then you'll have a very, very complex model, which should have a better quality, let's say, of synthetic data. But yeah, that is maybe one of the next steps. We started small for the moment, but yeah, that's a very, very, very good question.
Then
I think
the next.
I think this, just from Alison, I think this other thing is when you are basically bringing together, concentrating, we don't know what the word is, but when you bring in, when you combine the information from multiple companies together for GAN training, is the order of companies important, or have you found some architecture which is agnostic to the order of companies?
No, basically it's agnostic to the order. The entire architecture is agnostic to the order. It doesn't matter if you feed it with data now, or with this type of data now, or in the next 10 iterations, or in the order in which you take companies. But that is only valid in the second type of data set that I've mentioned. So only when we are taking the entire batch, the entire subset as a batch, not when randomly choosing companies.
Okay, so Teresa again.
Yeah. Which will be the performance of the model in the case of mixed asset classes with very different behavior? Any insights?
Oh, okay. We had some outliers, of course, but adding all of them together and basing our knowledge on the fact that they mostly behave the same, it's like a mean filter, meaning that you kind of reject all the outliers and you concentrate on how the mean behavior evolves for the companies. So you won't have any very different values from striking you out from, let's say, the normal behavior of the synthetic samples. So in some regard, you are kind of let's say throwing away the very big outliers with this type of processing.
Okay, then we have another one. How is this data generation different from predicting future prices?
Okay, when we generated these samples, we generated values for 250 days at the same time. What the question is concerned with is that you have 250 values and you want to generate the next one. We were not interested in the connection that the previous 250 days have to the 251st day, the 251st day, sorry. So the samples that we generate do not take into consideration the previous history of that company. It's just one batch of 250 samples. We are not interested in the before history or in the after history, such that we end up with a prediction framework.
Okay.
Then one last question. Could you claim that with the 50.04% of performance, we are actually confirming the efficient market hypothesis?
Yes, indeed. There was another interesting paper which tried 1 million different models, and the best prediction accuracy that they managed to achieve was 51.75%. But their training setup was in a much stricter framework than what we did. So adding more restrictions is guaranteeing a better accuracy. Whereas going into the open world and on real samples, of course the accuracy is sure to drop. So testing on real data and achieving 50.04% on the baseline, of course, guarantees this assumption. Yes.
Thank you very much. And then I also have a question, which is more a bit general and concerned a little bit the problems with the stock market. Every little thing in stock market can cause the stock market to crash or change drastically. And I'm just always wondering, or it makes the stock market kind of unpredictable. And for me, I just was wondering how you can, or can the AI learn the stock market if it's that unpredictable?
Well, this is funny because the AI does not have to learn how the stock market behaves, but how the people investing in the stock market behave, because this unpredictability comes from the people. So once you understand the behavior of the investors, then you can talk about stock market predictability. Because of course, if you hear some news, then you might be scared, and then you will, let's say, you sell all your assets. And a lot of people will do that, and that will cause a crash. And of course, as it happened before. So yeah, it's very difficult to predict the stock market. People have been trying to do this for 40 years, 50 years or so, and nobody has managed to find the perfect solution. There are a lot of models studying the behavior of people and how the market should behave, but they are not always right.
Yes. Okay, thank you very much. I think for today we're coming to the end.
Okay.
There is a question also. If you would share with us your PowerPoint.
Okay.
Would you
I
do
think
this?
isn't it shared right now?
Yeah, you share
sorry.
it.
You want me? Okay. You want me to share the presentation? Okay, sure.
It's up to you if you want to send it. No? But if yes, send it to me, and people who want to have it can ask. No?
Okay, perfect. Yeah.
And we will also have this recording ready after, of course, this cafe, and then we will send it to you, Mihai, and then you decide if we can basically publish it. It's up to you. No? It's always important also for the public to know. You decide, you give us then a green light if it's okay or not, and then we will have the recording published on YouTube as well as in the AI Cafe channels. Okay. So then again, thank you everybody. Thank you, Mihai, especially for your great presentation. It was a pleasure to have you here. And thank you to all the participants. Yes. And have a nice afternoon. No?
You too. Thank you. Bye.
Bye-bye.